Hi everyone, my name is Sophia Pedigo. I hope you're doing well. Today I'm going to be walking you through a problem in which we have a cylindrical cup, and that cup has some liquid in it at a height r, which is equal to the radius of the cup. Now what we're going to do is we're going to be rotating that cup at an angular velocity, omega. And what we're trying to find is what is the maximum angular velocity we can rotate this cup at before the liquid that's inside spills out. So as this cup is rotating, it's going to the liquid is going to take this parabolic-like shape, and we're going to be able to find what the maximum angular velocity is before that liquid spills out the edges of the cup. So to get us started, I have a couple of equations written down. Ultimately, what we're going to try to do is we're going to try to make substitutions in for this d term, the depression, and this h term, the height here, in order to solve for the maximum angular velocity. So that's what we're going towards with this. I'm going to start off looking at this equation here, which says the change in pressure over the change in the r coordinate is equal to the density of the liquid times the angular velocity squared times that r coordinate. So we can rearrange this a little bit and integrate both sides. We'll end up with the integral of 0 to p of dp prime is equal to the density times omega square integral of 0 to r of r prime dr. Now when we solve for that, we're going to end up with p equals the density omega squared times r squared over 2. We're going to make a substitution in for p, and that's just going to give us density times g times h. And let's go ahead and solve for h here. So when we do that, the densities are going to cancel out, and we'll end up with h equals omega squared r squared over 2g. And that's ultimately going to be the h that we substitute into this equation up here so we can solve for the maximum angular velocity. Now I'm going to go ahead and rewrite this equation over here so we can just set that to the side and work on finding an equation for this depression here. So I'll say that h at r is equal to the radius of the cup equals the angular velocity squared times the radius of the cup squared over 2g. And we can set that aside and come back to that. Next, what we're going to look at is this figure over here. So all we're going to do is look at this thin little slice. We have some change in radius and some change in volume. And we can say that an equation that represents that is the change in volume is equal to 2 pi h r dr. Now we can make a substitution in for our h. That doesn't look like an h, but it is. And we can actually substitute this in for it. So we'll end up with dv is equal to 2 pi multiplied by the angular velocity squared times r squared over 2g multiplied by r dr. We can take the integral of both sides. So that'll give us the integral of 0 to v of dv is equal to, the 2's cancel out, so we're left with pi omega squared over g times the integral of 0 to r, capital R, of r cubed dr. So we'll take the integral of both sides. We end up with v is equal to pi times the angular velocity squared over g times the radius to the 4th over 4. And now we have this v term, and we actually can make a substitution in for this volume here. And the way that I've gotten this equation is I looked up here and I saw that this volume over here, which is like half of the height, this red part here, is actually equal to the volume of the top half of this parabola. And that's equal to pi r squared d. So we can make a substitution in for the v here, and that's how we can solve for this depression term here, d. So we'll say that pi r squared d is equal to pi omega squared g times r to the fourth over 4. Now we can go ahead and solve for d, so we can make that substitution. And when we do that, we'll end up with d equals, the pi's cancel out, so we won't have that term anymore. We'll have omega squared. 2 of those r's are going to cancel out, so we'll have r squared. And then we'll have g times 4, or 4g. So now that we have the 2 little bits of this equation that we were trying to solve for, we can make that substitution and solve for the maximum angular velocity. So when we do that, we'll have this height here equals the radius, or the height of the cup, minus the distance, or the depression here that we just solved for, which is omega squared radius squared over 4g. And then this term here, which is plus h, so plus omega squared r squared over 2g. We'll multiply this term by 2. That'll give us h equals r minus omega squared r squared 4g plus we can combine, oops, that should be a 4. We can combine like terms here so that we end up with h equals r minus, no, plus omega squared r squared over 4g. And now we can solve for that omega squared, and that's going to give us the maximum angular velocity. So moving over here, we can say omega squared times the radius squared over 4g is equal to h minus r. Multiply both sides by 4g. Angular velocity squared, radius squared, is equal to h minus r times 4g. Divide both sides by the r squared. Angular velocity is equal to 4g h minus r over r squared. Then we just take the square root of both sides. And our maximum angular velocity is going to be equal to 4g, the square root of 4g minus h, or the square root of 4g multiplied by h minus r over r squared. And we can further simplify this just a little bit to get the angular velocity is equal to 2 over the radius multiplied by g, the square root of g, times h minus r. And that is going to give us the maximum angular velocity that we can rotate this cup without the liquid spilling out.